Hey everyone, Grayson here with another based theory. Today, I want to talk about what could be a potentially new law in physics, the holographic principle and ADS CFT correspondence. Or, in other words, is the universe a hologram? Now, to answer this question, we're going to have to talk a little bit more about what holograms actually are. Lots of people are familiar in a colloquial sense with holograms, like everybody knows the hologram Tupac that gave a concert live a few years ago, and people I'm sure are familiar with holographic trading cards, like holographic Pokemon cards. But what actually makes these things hologram? What do we mean when we say hologram? Well, specifically, some of these things, like a holographic Pokemon card, are not true holograms. There are illusory holograms. But generally, a hologram is something that can represent a higher dimensional information in lower dimensional space. So typically, that's a two-dimensional object that encodes all the three-dimensional information about an object. So with Pokemon cards, it gives the illusion that there's a three-dimensionality aspect to the image on the card. Now, this is only an illusion and not a true hologram, but the principle itself applies, and you can understand what a hologram is intuitively when you just think, a hologram is X dimensions, but represents X plus 1, X plus 2. A higher dimensional information is contained within a smaller dimensional space. Now, for years, holograms were relegated as a kind of niche novelty idea, and we're not really seeing much of a mainstream impact on science and specifically in physics. But that all began to change in the 1970s and 80s when Jacob Bekenstein first discovered that the amount of entropy in a black hole, which is related to the amount of information that a black hole contains, does not vary with the volume of the black hole, which would be what we would be intuit maybe, but instead varies with the area, the surface area of the black hole. Now, this is very strange when you think about it, because you would think that the total amount of information would be contained within voxels, which is three-dimensional pixels. But de Hoof's calculation showed us that it's actually dependent on pixels, two-dimensional bits of information rather than three-dimensional bits of information. And that is what sets the hard limit on the amount of information that a black hole can contain. It's not anything inherent to the three-dimensional aspects of the black hole, but the two-dimensional. Now, this opened the floodgates, and physicists, like one of my personal favorite physicists, Leonard Susskind, took this holographic principle idea and began developing it to apply in black holes and string theory more broadly. The holographic principle may just be the most newly discovered law in physics. Now, the reason we have to say it's potentially a law is, of course, because these things are not yet experimentally verified. But in a theoretical sense, with the mathematics at least, they have proved to be absolutely axiomatic and behave in the way that other physical laws do. But what exactly does the holographic principle state? Because the holographic principle does not just apply to black holes. The mathematics surrounding black holes were instrumental in the development of the holographic principle, but the holographic principle applies more generally to any three-dimensional space, like this room that I'm in right now, where all of the information for everything contained within this room, me, the computer, this light, everything within this room the information is encoded within the borders of this room. And this applies to any three-dimensional space. If just this little cube of air right here would have a boundary in which all the information in the interior of that cube is encoded within the information on that boundary layer. This is the holographic principle. The 2D borders of a three-dimensional space encode all of the information necessary to know everything about it, the interior of that space. All the information is contained within the borders. Or, in the case of a black hole, what we would refer to as the black hole's horizon. Now, the most successful realization of the holographic principle came in 1997 when an Argentinian physicist named Juan Maldacena first laid out the mathematical framework of what would later be known as ADS CFT correspondence. Now, this is a highly complicated and mathematically dense concept that involves a lot of high energy physics and string theory, but I'm going to try to simplify it as best as I can. The correspondence is between ADS, which stands for anti-de Sitter space, and CFT, which is a conformal field theory. Now, anti-de Sitter space is not like the normal space that you and I are familiar with. The distance between two objects is not a simple calculation with our understanding of what space is. The distance between 2 points in anti-de Sitter space is a result of a series of mathematical steps or iterative operations. So it doesn't at all look anything like we would consider as normal three-dimensional space. In fact, because as you get more and more distant in anti-de Sitter space, what you're essentially getting is more and more complicated a series of mathematical steps. You're increasing the complexity with distance. So this leads to a number of really weird, interesting properties. For example, if we imagined a flat disk in anti-de Sitter space, the border of that disk would be infinitely far away from all of the points in the interior. And this makes sense if you think about it, because if you need to get to the border, right, the amount of steps, iterative mathematical processes that you have to go through becomes infinite. So the border of an anti-de Sitter space is infinitely far away from all the points in the interior. Now, if we stack these anti-de Sitter spaces with time, right? If we arrange them in a higher dimensionality to represent time as a third dimension, then we get something very, very interesting indeed. We get something that resembles a cylinder, the outside surface area of which is the border of all these anti-de Sitter spaces, which again is infinitely far away from all the points within that cylinder. And something very, very interesting emerges when you have a conformal field theory on the surface of this anti-de Sitter space. Now, you can have the conformal field theory, which represents our normal quantum field theories of corresponding to the particles as we know them minus gravity, right? There's no gravity in our current understanding of quantum mechanics. But if we have our current quantum physics playing out as we understand it on the surface of this anti-de Sitter space, what Juan Maldacena showed is that on the interior of this space, within the anti-de Sitter space itself, what we find is that in the higher dimensions, gravity naturally emerges. Now, this is really exciting because it's potentially hinting at a unity between gravity and the quantum world, which has been the grand prize in physics for over a generation now. Juan Maldacena showed that quantum physics operating in a two-dimensional space, like two dimensions of space, one dimension of time, can correlate within a higher dimensions of space to gravity, to something that resembles more of our current universe. Now, within Juan Maldacena's framework, the exact anti-de Sitter space is a higher dimensional than our normal space, so it doesn't quite resemble our universe yet. But mathematicians and physicists have been attempting to render a more generalized theory of ADS-CFT correspondence that does look like our normal universe. And at the very least, this mathematics at least lays out a framework for describing in a rigorous way how this holographic principle can be realized, and that everything about our universe, including gravity, which so far has eluded our quantum physical descriptions, can emerge from two dimensions of physics. In fact, it hints that everything about our universe can be completely described in a lower dimensional, more fundamental reality than the one that we are familiar with in our everyday lives. In fact, the physicist Leonard Susskind himself said that the three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant two-dimensional surface. The holographic principle would imply that our universe itself has a distant horizon in which all of the information within this universe is encoded. Thus, physically and mathematically, the universe itself is a hologram. Now, as I mentioned, this is still new physics. All of the dates for all of these discoveries that I was listed were in the 90s and the 2000s, and we're still learning more today. So this is very much on the pioneering edge of physics. But just to show you how much excitement is around these ideas and how seriously the physics community is paying attention to these mathematics, Juan Maldaceno's paper is the most highly cited paper in all of high energy physics. Over 23,000 citations today and climbing. And the vast majority of all of these citations have been within the last 10 years. So this is a hot area of research in current theoretical physics and string theory. But I'd like to pose a further question, another based theory, if you will. If the universe, mathematically and physically, has a horizon in which all of the information within the universe is contained, and black holes have a horizon in which all of the information within the black hole is contained, could our universe be residing within a black hole? Could our universe be a holographic representation of the actual physics that's going on the surface of a black hole? Well, to answer this question, we're going to need to learn a lot more about the way that black holes work, both theoretically and experimentally. But in the next few years, as our observational technology continues to improve, we may just discover things about the universe and black holes that blow all of our minds. Thanks for watching another Based Theory, guys. This was a lot of fun to make, and I'm looking forward to the next one, which will be discussing all of the strangest mammals and mammalia forms in the dinosaur era. So look forward to that. Stay tuned for more. Remember to like, share, and subscribe. It means a lot to me. Thanks.